Hello everyone, welcome to yet another session of Nanoelectronics Module 6. In the previous session, we discussed about MODFET, the modulation doped field effect transistors, also called the high electron mobility transistors, HEMT or MODFET. In today's session, we shall focus about another device, the heterojunction bipolar transistors or HBT. So today's session is about heterojunction bipolar transistors. We all are familiar with our normal BJTs, the bipolar junction transistors, right? The main application of BJTs are amplifiers, which means they must have a very good amplification factor, and we also must know their frequency of operation, right? So basically for a BJT, we prefer a very high value for the amplification factor beta up to the largest frequency possible. And the maximum operating frequency of this BJTs depends upon various parameters. It may be the geometrical dimension of your device, the doping levels in the emitter base collector regions. In fact, these parameters determine the operating frequency of your BJT. And if you want to get an extremely high value for the amplification factor beta, we must make sure that the current gain through the base, alpha, and also the injection efficiency factor for the emitter, gamma, must be as close as possible to unity. So if you recollect, whenever we are studying about BJTs and their configurations, we always said that alpha must be nearly equal to 1. And whenever we were doing any analysis, we always took it as 0.9995. So it was approximately 1. Same was the case of gamma, the injection efficiency. And beta had a huge value, more than 50s or 100, 200 range, right? So if you want to make beta extremely high, we ensure that alpha is nearly equal to 1 or as close as possible to 1, as well as same the case of gamma also. Now, in order to ensure this condition, what must we do? So, in order to ensure this condition, we make sure that the emitter region doping must be higher than the base region. We always try to ensure that, right? We make sure that the emitter's doping level must be higher than that of the base region. However, still there is a reduction in the energy gap of the semiconductors, see, when the doping level is very high. And because of this reason, right after the invention of our BJTs, our normal BJTs, it was a researcher Shockley who suggested that the emitter could be fabricated by using another semiconductor of a wider band gap. So we had a conventional BJTs in which we took maybe silicon, just silicon was the material. In two regions we doped it with N-type materials, and the mid portion we had the P-type materials. They have two junctions, yet the junctions are homo junctions, right, because of the same materials. Now it was Shockley's suggestion, why can't we replace the emitter region by another semiconductor of a wider band gap? Now what is the advantage of this? If the emitter is of a wider band gap semiconductor, this would reduce the amount of injected carriers from the base to the emitter region. And when this happens, you can improve your injection efficiency of the emitter. And when the bipolar transistors were fabricated by using this technique or by using another semiconductor of a wider band gap for the emitter region, this created a new type of bipolar transistor called the heterostructure bipolar transistors, HBT. We can see the diagrams of a homojunction of a conventional bipolar transistors and a heterojunction bipolar transistors. See, when I say HBTs, it may be heterostructure, heterojunction, both the names they go together, right? Both are the same. So don't get confused when I say like I may interchange this heterostructure, heterojunction, both are the same, right? Okay. So see here in figure A, we can see the homojunction bipolar transistors, and homojunction bipolar transistors are nothing but your conventional BJTs. And in the second figure, you can see your heterojunction bipolar transistors, or our device of concern right now, the HBTs. Now, we can see that in the case of the heterojunction bipolar transistors, the band gap of the emitter is larger than the base region, isn't it? And because of this, the barrier for the injection of electrons from the emitter to the base is lower than the corresponding to the holes. And because of this, we can get a great increase in the amplification factor beta. What have we observed? We have seen that for homojunction, see, these barriers in the emitters are the same, right? But in this case, the band gap of the emitter is larger than that of the base region, NPN, emitter base collector, right? So the emitter was having a larger band gap than the base region, because of which we could increase our amplification factor. And in fact, this barrier height has a great influence on the carrier injection through the emitter base junction. See the injection of electrons has I have to say a nearly exponential dependence on the barrier height. See, because we can say that beta is proportional to delta Eg by kT, where delta Eg is your difference in the energy level between the wide bandgap emitter and your narrow bandgap base region, and kT, which is a constant. K is your Boltzmann constant and T is your temperature, and at room temperature the value of kT is nearly 0.026 electron volt, and the small gap between delta Eg in fact increases the beta factor, right? So we can see that the beta factor is partially exponential with respect to your delta Eg. And all these factors, they show that our heterostructure bipolar transistors, they have a pretty good margin for fabricating, if you want to fabricate heavily doped base transistors with a very low value of the base resistance and low value for electron transit time. So HBTs can be used for fabricating such type of devices, right? And see, we must also ensure that the doping of the emitter, which can be reduced, and this results in a smaller parasitic capacitance with respect to your emitter base junction. This reduction must be simultaneous, right? What is that? As you reduce the doping of your emitter region, there must be a corresponding reduction in the parasitic capacitance in the emitter base region. And it is in fact this reduction, this simultaneous reduction, which affects the performance of our HBTs at very high frequencies, because we know that it is at higher frequencies the parasitic capacitance come into effect. So as you reduce the doping at the emitter, your parasitic capacitance too must reduce, which will affect the performance, in fact not affect, which will boost the performance of the HBT at high frequencies. Now, see, we have seen the band diagram of a homojunction and a heterojunction transistors. Now, what makes this heterojunction transistors very important is that we can modulate or manipulate the base of these HBTs. And what can we do? We can make graded base HBTs with like varying band gaps from the emitter to the collector region. Let's see the diagram. See, this is a graded base HBT. This is the base region. We have a base region of diminishing, of reducing band gap from the emitter. This is the emitter section, right? Emitter, base, collector. From the emitter to the collector, the band gap of the base material is reducing. This kind of HBT is HBT with graded base region. Now, because of this, what happens? Because of this, there is an internal electric field, and this internal electric field will further accelerate the electrons traveling from the base region, and this can in fact help the HBT to operate at even higher frequencies. See, already the HBTs are good at very high frequencies. We just have to control the doping at the emitter. We have to reduce it, parasitic capacitance reduces, and the performance of HBTs at higher frequencies improves. There is another technique to improve their HBT high frequency performance, that is by using graded base, right? So the base is reducing from the emitter to collector. That is an important point. From the emitter region to the collector region, the band gap is continuously reducing. Now, see, here we have fabricated the emitter with a semiconductor of wider band gap. Now, what if the collector region is also fabricated from a wide band gap semiconductor? If the collector is also fabricated with a wide band semiconductor, the breakdown voltage, you are familiar with the breakdown voltage, right? The breakdown voltage of the base collector junction, can be further increased. So this is the HBTs with a wider band gap collector region too, right? So when this is done, we can see that the breakdown voltage of this junction increases, and this structure is called a double HBT. Why double HBT? Both the emitter and the collector regions are fabricated with a wide band gap semiconductor. Yes, I hope this is clear. What is HBT? Normal BJTs with your emitter region fabricated with a wide band gap semiconductor. Why this is done? How does it improve the amplification factor? Other possibilities for modifying the structure? That's what we have seen so far, right? Okay, let's continue. Now, see, when I say a heterojunction, the image that comes into our mind is the aluminum gallium arsenide and gallium arsenide heterojunction. And this particular heterojunction is so efficient and they have excellent mobility factors. So we also always prefer fabricating HBTs with these kinds of semiconductors. Not always aluminum gallium arsenide and gallium arsenide, it may be also any other third, fifth group compounds. So typically when we fabricate these HBTs, we make sure that the base length is about say 50 nanometers and it is heavily doped. And the doping may be about say 10 raised to 19 particles per centimeter cube. And you can use these transistors to frequencies up to 100 gigahertz, which is similar to your MOSFET's operation range. And you can see, in fact, this 100 gigahertz is a very high frequency when we compare it with the silicon MOSFETs. Silicon MOSFETs can't even think about operating at such a high frequency range. So you can use HBTs for high frequency operation. And now if you change the materials, if you are using indium kind of indium materials in your heterojunction, indium gallium arsenide or indium aluminum arsenide, or even indium gallium arsenide and indium phosphide heterostructures, you can further increase your operating frequencies. It can reach about 200 gigahertz. And another feature of your HBT is that we can use these in various electronic and photoelectronic devices, and we shall see that in the coming sections too. Now we have seen what are HBTs, how is it different from BJTs, and we just said that the common material used for HBTs is aluminum gallium arsenide and gallium arsenide. But the researchers are being focused on developing various other kinds of HBTs which are based on silicon. See, silicon is the very core of our semiconductor industry. We just can't let off silicon. It's one reason for that is also their easy availability, right? It's tough to manufacture this third, fifth compounds. Though they have beautiful properties, it's a bit difficult to manufacture them. So we always think about how can we still manipulate silicon. So present research is going on silicon type compounds. So we have various silicon compounds of wider band gap, and one such compound is silicon carbide, SiC, and they have a band gap of 2.2 electron volt. So if we recollect, the band gap of aluminum gallium arsenide was nearly 2 electron volt. So this is higher than that, right? And we have another material that we use is hydrogenated amorphous silicon, whose band gap of 1.6 electron volt. Again similar to that of gallium arsenide. So replacing our conventional aluminum gallium arsenide with new silicon compounds research is still going on. This can also develop new kinds of HBTs. Who knows? In the future we may have to study those compounds too, right? And apart from the silicon carbide or amorphous silicon, we have another silicon based compound, that is none other than the silicon germanium based alloys. We are already familiar with the silicon germanium compounds, right? So we have that the band gap of silicon is 1.12 electron volt, and while that of germanium is 0.66 electron volt. So the silicon germanium heterostructures can be manufactured or can be developed for fabricating HBTs. Now for fabricating the silicon germanium based HBTs, what we prefer is the silicon will be the emitter region, right? The silicon will be your emitter region, and that will be followed by silicon germanium based region. And so there is a band gap energy. The band gap energy of silicon germanium is smaller than that of silicon. And this band gap energy difference will allow the doping of the base region with very high concentration, which in fact allows operation at very high frequencies. So normally the HBTs, so we have said that HBTs work up to a frequency of 100 gigahertz. Their cutoff frequency is nearly 100 gigahertz. But with such kind of devices like silicon germanium devices, we may be able to extend this cutoff frequency to up to 400 gigahertz. Who knows? And in these compounds, the silicon germanium strained layer type compounds, the electron mobility is also increased by say 60%. So all these factors or all these possibilities give us a new direction for research. Rather than the very commonly used aluminum gallium arsenide and gallium arsenide HBTs, we can also think about silicon based HBTs. It may be silicon carbide or most importantly the silicon germanium. Now when it comes to compound semiconductors, there is a factor of mole fraction X, right? So by changing this value of X, we can make the silicon germanium based HBTs the gradual base region kind of HBTs also. We can continuously change the band gap as we have seen earlier, the double HBTs, right? So we can also modify the silicon germanium HBTs in that manner. But we have seen that these HBTs have a higher power dissipation than MOSFET, which is a disadvantage definitely, right? But at the cost of higher dissipation, we can get better operation at high frequencies with lower noise. So there is definitely a trade-off. What do you prefer? Do you prefer better operation at high frequencies with low noise, or is it the power dissipation you are concerned? So based on that, you will select what kind of HB devices you need. If you can tolerate the power dissipation, you can definitely prefer HBTs for high frequency operations. So due to all these factors, we prefer silicon germanium based HBTs maybe in the near future, right? So that's for this session. This session was all about HBTs, the heterostructure or the heterojunction bipolar transistors. We saw how is it different from the conventional BJTs, what is a HBT, how is it fabricated, and different types of HBTs, how they can be a gradual base HBT, how they can be a double HBT. So those things, and what are the compounds that we are commonly using for HBTs. So we discussed all these factors, and I hope this is clear so far. Please go through it, and if any doubts, please let me know. Thank you.